lecture, I'll talk about the energy system. Previous lecture, I talk about the uh, definition and what kind of type of energy system available. I'll say there is a fossil fuel-based type energy system versus renewable type energy system, or you can classify as a relatively large-scale energy system like a power plant versus the small-scale energy system like a solar cell or fuel cell. Also, you can classify as a centralized system. So far, we using this kind of system since the modern days, like uh, very big power plant, nuclear power plant, and thermal, coal and natural gas, petroleum power plant, versus a distributed system that is comparatively small system, and like yeah, solar cell, fuel cell, and small units. Also, I discuss about there's a problems in a system. There's a domain problem, and there's a scale problem and limitation problem. The energy source is always limited. However, most important problem of energy system is the sustainability. So if we need the energy system, all human and all country and everybody need an energy system. Yeah, yeah. For example, in the morning, yeah, you have an energy system. Yeah, you in the morning you you start yeah you have a start air conditioning or cooking or the transportation, whatever. That's all energy system. So the problem is, yeah, to operate the energy system with a sustainable way. That's the problem. To operate or design or the design or whatever of the energy system sustainable way, you need to analyze the energy system. So through the analyze, you will yeah you will find there's a highest efficiency energy system and the operating condition. So that can be done by the analysis system energy system. Also, the most of the energy system is used in the engineering. Engineering is can be defined as yeah some relocation of the natural source, so to improve the to improve the human human interest. So example, yeah, if you build a yeah, I mean hydropower facility, yeah, the hydropower facility using uh, water from the river runs, yeah, river runs, and using the water. You need because it's a potential energy. You need as high as the height of the difference between the top place and bottom place. Also, you need a large amount of as large as amount water you require to get hydropowers. To do that, so you need to build a dam. What's the height of dam, and the amount of the dam structure. How you build the dam structure. That's engineering. So that's a relocation of the natural source. That the water runs through the river. That's a natural source. If you make a dam, that's with the dam construction, that's a relocation of the natural source, right? That the dam construction involves the engineering. That's energy system. Through the engineering, energy system should be analyzed also, and yeah, you find the optimum solution of that. So in this lecture, I usually talking about how you do the what kind of method you can apply on the energy system. So that I mean, this lecture is mainly based on the analysis of the energy system. Maybe I have some other lecture, yeah, based on the design of energy system. Analysis design is relatively different. Analysis has a very very short range of the answer.
City,
Analysis,
why
yeah,
I'm
there
not
is
a
only one
Christian.
answer, or maybe two or three answers. However, design, there's many different design is available for the purpose of the energy system. So design is much varied compared to analysis. I show you later what is the design of the energy system. So the energy system premise, within the energy system, usually we say energy conversion and energy transfer is occurs. Energy transfer, conversion and transfer of the heat energy and work energy. So, for example, you know the car. Car is the we call that as a gasoline engine. This is a car engine. Cylinder is moving. This is cylinder moving, and there's a what? There's a gasoline and air coming in, and that is combusted. So gasoline is chemical energy. Once it combusted, then it became thermal energy. Then the thermal energy is causing the moving the piston. That's a mechanical energy. There's energy conversion. It's chemical energy and thermal energy to mechanical energy. In the power plant, same thing. This is the power plant, and you put in the coal, that's a chemical energy. Coal burning, that's a thermal energy. And that is changed into the steam energy, that's also thermal energy. And that turns the steam turbine, that's a mechanical energy. And mechanical energy is generate electrical energy in the electric generator. So there is always the energy conversion. Conversion take place in the energy system. For this case, thermal energy from the flue gas to the thermal energy of the steam, that will be done at the heat exchanger with the boiler surface, superheater, reheater, whatever. That's the heat transfer. So in the energy system, there is always energy conversion and energy transfer take place. Usually, energy system, conversion of the primary and secondary energy. In this case, the secondary energy is the electricity, primary energy is the coal. In this case, maybe secondary, I mean, this is not a good example. And if you have a refinery of the petroleum, you put the petroleum and you produce a gasoline, diesel, whatever. In this case, petroleum is the primary energy, and gasoline, diesel is the secondary energy. So primary energy means the energy itself existed naturally, like a coal, natural gas, and the petroleum. Secondary energy is from the primary energy we convert into the secondary energy form to make use for the human interest, like electricity, gasoline, diesel is the category of the secondary energy. So the energy system premise, another energy system premise is the production of the useful type of energy. That's I already explained to you. Electricity, that's useful to human, and gasoline, diesel, that's useful to human. Here, mechanical, electrical, heat energy, and efficiency is most important in the energy system. So there is a many different type of the energy system, like a steam boiler, internal combustion engine, like a gasoline engine and diesel engine, gas turbine and steam turbine, refrigerator, nuclear reactor, solar energy system, fuel cell, light emitting diode insulator. That's all maybe there's a more analysis. I introduced in the first lecture, yeah, previous lecture of the various energy system. However, I say here most important thing is efficiency. So I think next no, I show you there's a efficiency of the different energy system like there's a very low efficiency incandescent lamp and very high efficiency like electric motor or electric generator. Then how you describe the efficiency? How you define the efficiency? Efficiency is yeah, usually efficiency is efficiency usually then denote as a type equal to something in input, right? And input is yeah, input we is with compared with something output or output, but output should be useful to humans. So you say we say useful output, useful output. So efficiency is comparing between the input and the useful output. So energy conversion efficiency, energy type is not, yeah, previously I talked to you thermal, chemical energy change into the thermal energy, mechanical energy, electrical energy. And you know the energy through this conversion, or the conversion energy is conserved. That's the first law of energy, first law of thermodynamics, energy conservation. So initial energy equal to final energy, E2 plus E3. Here E1 is the input energy, E2 is the waste energy. That's not useful to human. So E3 is energy, the energy output useful to human. So the energy conversion efficiency is expressed like E1 divided by E3, input energy divided by useful output energy. I already talked to you, there is many different energy type, and the efficiency is very small, like incandescent lamp, and there's a fluorescence lamp only 20%. So we need to go this illuminating device change into some other thing yeah, in the future, and that is it is going on right now. They start to change this one into the LED, light emission diode. Also, you know, change into the small heat engine. I mean, small efficiency, relatively low number of the heat engine efficiency, like a steam engine, IC engine, into the higher one. So you wanna change into this small, low efficiency group to the large efficiency group in the future. So that in the energy conversion, the heat energy is most of the energy conversion system of the fossil fuel based energy system is going with the combustion. So once you make a combustion, the chemical energy is changed into heat energy. So heat energy is the key process of the energy conversion, like automobile. Chemical energy of the gasoline is combusted and became a heat energy, and that heat energy moving the piston and the piston of the mechanical energy. In the power plant, chemical energy of the coal is combusted, and that through the combustion heat energy, thermal energy or heat energy is generated, and that is became a steam, and steam rotating the steam turbine, that is mechanical energy. So in the energy conversion, combustion is very important, and then within this combustion process, usually they say the pollution. I mean, air pollution product was generated. So when you are talking about what kind of the pollutant to generate from this energy system, you need to looking this side combustion. And the efficiency, most of the combustion efficiency, I think is maybe greater than 90-95%. Then once you make thermal energy, then thermal energy became the conversion to the mechanical energy, and there's efficiency limitation. Automobile, most of those efficiency from heat energy to mechanical energy is less than 40%. So if you are looking for the efficiency, improve the efficiency like that, you will look at this conversion process. So whatever the pollutant efficiency, you need to know the thermodynamics, like how much CO2 is generated, CO2 greenhouse gas. Yeah, you calculate from the fuel how much in the fuel, how much carbon, and through the carbon you calculate how much CO2 is generated, produced of the this energy system. That's we call the thermochemistry. That's thermodynamics, and those things. CO2 and CO also you produce CO and H2, H2O, and nitrogen, and the the component percentage of this, they will be depends on the temperature. So what kind of temperature of the combustion after the combustion? That's the thermodynamics. Yeah, I'll show you later. I mean, input energy is same to output energy. So through the thermodynamics, you can calculate the final temperature. So you need some knowledge of the thermodynamics. Thermodynamics is a study of conversion process between heat energy and other type of energy. Also, yeah, thermodynamics, the big assumption is energy conservation. And to make a conversion useful, the energy transfer and conversion should occur with predetermined process and direction. I mean, predetermined the heat flow. The heat is usually heat is flowing from the high temperature to the low temperature, like same thing. Water flow from the higher state to the lower state, higher position to lower position, same thing. The heat is flowing from the higher temperature region to lower temperature region and produce the work energy. That's the direction. And predetermined process, process like this one. This is a combustion process. This is a bottom one is the steam turbine rotating process. This piston moving process. So you need what kind of process, what kind of direction, and different process, different direction, and you can optimize the efficiency of the energy system. So principal energy, so you need a model of the energy conversion process energy system. So energy system you can describe it like this: input energy, output energy. Output energy can be waste energy and useful energy, and there's energy conversion process like a combustion and steam turbine, gas turbine. That's physical phenomena. And the piston is moving, and then the steam turbine shaft is rotating. That's all the physical phenomena. And you want to analyze this energy system because you need to operate this system as much as possible sustainable way. So you need to analyze this energy system. How you done this? By experiment? No. You need to make a model first. Experiment, yeah. So if you do the experiment something wrong, there's always accident happen, right? The pollutant generation, some safety problem. Also, experiment means it's a money, labor cost and utility cost is required. So you need to make a model first with mathematics with the aid of the computer. So output energy or the efficiency is a function of input energy and other parameter. You can make a function like efficiency equal to function of temperature, pressure, input energy, whatever, and many different parameters is depends on the efficiency. So you want to make then there's a more than one parameter and 3 or 4 parameter. You need more than one equation, right? So 3 or 4 equations, and then you need to find out the equation between the temperature and pressure, temperature and energy, input output. You can make an equation. Such equation or function based on the theory of low of the energy system. Most widely using low energy system, conservation of low energy conservation. Based on the theory like conduction heat transfer, radiation heat transfer. That kind of that all of this individual equation is integrated together. You can make a mathematical model. Through that model, then you can find out the analysis and what happened. If you change input energy, then what happened? How the efficiency? If you change the temperature, if you change the pressure of this energy conversion process, what happened? So that's we call that as a model. So an energy system is an engineering model based on the thermodynamics is required. So I said you need the basic law of energy system required, or some basic theory is required for to develop the mathematical model. The most widely used basic law of the thermodynamics is the first law of thermodynamics. Everybody knows that's energy conversion, energy conservation. Heat is equal internal energy plus work. Heat is internal energy plus work. Q equal du plus dw. That's first law of thermodynamics. Also, you can write down delta U equal Q minus W. This is the derivative form of the same thing, right? So here U is the internal energy. Internal energy is only function of temperature. What they say, if you are sitting in the room right now, listen my lectures, and the room temperature increase, then internal energy of your air is increase. Room temperature decrease, internal air is decrease. And through those things, and Q and W is equal, that's first law of thermodynamics. Second law of thermodynamics, you can tell second law of thermodynamics in many different ways, right? With the second law of thermodynamics, you need to find out entropy. So this is entropy. And also you need to talk about efficiency in the thermodynamic law. So that there is some conversion, energy conversion. Some conversion is relatively easy, some conversion is relatively difficult. So the work energy to heat energy conversion is difficult, and heat energy to work energy is easy. No, it's the other way. The work energy conversion to heat energy is heat energy is easy, and heat energy to work energy is difficult. So that the work energy to heat energy conversion is more than 95%, and heat energy to work energy conversion is less than, let's say, 40%. Okay, so maximize the heat to work conversion. Most of the heat engine is a heat engine. What is the heat engine? Heat energy conversion to the work energy. That's we call the heat engine. Gasoline engine, diesel engine, steam turbine, gas turbine. Most of the energy system we are using based on the fossil fuel, that is heat engine. So you need to maximize the conversion, work conversion in the heat engine. Then the optimum design is required. Transfer of heat energy. They say the direction. I already said. I already said to you. Yeah, you must go to predetermine here. A predetermined process or predetermined direction. So this is a predetermined direction to make a heat engine. Yeah, heat should be flow down from the high temperature source to the low temperature source and produce work. So that the heat efficiency is W divided by the Q1. Refrigeration system, that's heat direction, predetermined heat direction the other way. Low temperature from the low temperature to the high temperature, and because same thing, water flowing from the higher state to the lower state, there's a spontaneous and produce the work. Yeah, the hydropower. However, if you transfer from the water from the lower state to the higher state, you need some pump. Otherwise saying you need some work. Same thing. To transfer from the low temperature heat from the low temperature to the high temperature, you need the work. So that in this case, work is required. They transfer low temperature to high temperature. We call that as instead. At this time, we call instead of the efficiency, we using the coefficient of performance, because sometimes it's greater than 1. Coefficient of performance equal to Q2 divided by W. So here the heat transfer, high temperature, low temperature is spontaneous. Low temperature resource to the high temperature resource require work, like in refrigerator, air conditioning, or heat pump, the same application. So the analysis heat pump, yeah, if you want to analyze this heat energy system, I think this is, let's say, steam turbine or gas turbine. Steam turbine, yeah, let's say this is a steam turbine. Steam turbine usually compose a pump. A pump, steam turbine, you can draw down like this: pump, then boiler, then steam turbine, then condenser. Okay, this is steam turbine. So water is flowing through this way. That means counter clockwise. That's the clockwise direction. I mean the other way, like a refrigerator and air condition is counterclockwise, the other way. So that at the pump, water is introduced and pressurized up to 150 atmosphere, 150 atm usually, and modern steam turbine more than that. Then that pressurized water, going into this boiler, and boiler receives some heat energy through the coal combustion or nuclear reactor. Because the water received the heat energy, it became steam. So the high temperature, high pressure steam passes into the steam turbine. Then the design of the steam turbine. Steam turbine has a shaft and disc. There's a shaft and discs. There's many discs are located, and the design of disc that the flow is passing through, then this is rotating, then produce electricity. And at the end of the steam turbine, you have a low temperature, low pressure, steam plus water. Steam plus water. Then you need to pressurize again all of this, all of the mixture to this high 150 atmosphere. You need to make all of this steam plus water to water at the condenser. So water gives you the Q2, and boiler receives the Q1. And here the steam turbine produces work like that. So efficiency equal to Q1 divided by W like this. So you want to analyze this, right? So what's the efficiency? Then you need to know how much is the Q1, how much is the W. Okay, to do that, yeah, you need to draw the phase diagram. I erase this. Okay, phase diagram. If you draw the phase diagram, the water phase diagram means the pressure and volume. Yeah, with the different pressure and different volume, phase diagram means water has 3 different phases, right? Solid, liquid, and gas. If you draw the phase diagram of water, it looks like this. Here is a liquid state, the liquid plus steam state, here steam state. If you draw this one, I said at the pump or what? The water is pressurized up to 1 atmosphere to 150 atmosphere. Okay, you can draw like this. So this is point 1, this is point 2, and this is 1 and 2. This is a perpendicular line. So you know that if you pressurize the water volume doesn't change because it's a liquid. So you can draw down like that. And at the boiler, that is position 3. Boiler, you receive the heat energy, and you receive the heat energy, and heat is because water received the heat, it became steam, and start to make a steam first, and there's a steam and water steam mixture exists in this state, and almost 100% steam position. That's we call the 3 point. That we call that a saturated steam state. And at the 4, if this position is a 4 steam turbine, and at the steam turbine, high pressure, high temperature steam is introduced, and it rotates and give the energy to the electric production, and this is a point 4. That's was this state. Water and steam coexisted. Then go back to original point. So if you draw down this kind of phase diagram, efficiency equal to, there's a Q1, this is Q1 coming in, this is Q2, waste heat, this is W coming out. So if you want to calculate Q1 W, if you want to calculate Q1, this is Q1, right? Then you know the enthalpy of this state, enthalpy of this state, and you can calculate W. If you know the enthalpy of this state, enthalpy of this state, you can calculate W and you calculate Q1. So that's we call the analysis. So this state, that's 150 atmosphere, 150 ATM, enthalpy of the water, enthalpy of the 100% steam. And here it is a mixture. How much of the mixture you can find through the state 3 and state 4 has the same entropy because it's isentropy expansion. So condition of the same entropy, you can find out how much of the steam, how much is, water exists at point 4. Through that, you can calculate the enthalpy of the point 4, enthalpy of the point 3, and you can calculate W. That's what we call the analysis. Okay, I erase this. So the component of the energy system is working principle cycle. Yeah, cycling motion. Cycle means process coming back to original state. 4 component element: boiler, turbine, and condenser pump. High temperature source is the usually combustion fuel. It's this much, 1500, 2000 K. However, you know, the boiler temperature is more important because, yeah, at the boiler, this high temperature source has a heat transfer to the boiler. So, yeah, well, how the boiler is made with the steel. Yeah, steel at this high pressure. I mean, withstanding temperature right now so far. Maximum temperature 650 degrees C. So that's high temperature. Low temperature sink is outside temperature 300 K. Working fluid, steam for the steam turbine. Water for the steam turbine. Or if you go to gas turbine, flue gas. So you can assume that the air. That's the working fluid. Most of the working fluid, flue gas and steam. The important thing between this and this. Steam, water has a phase change. The water became steam, steam became water. However, air or flue gas, there is no phase change within the cycle. So that's so that the type of the heat source, there's two different heat generation type, heat transfer type. Heat generation type within itself, heat is generated. Like internal combustion engine, heat is generated within the piston, gas turbine combustor, and fluid type nuclear reactor, chemical reactor. That's a heat generator type. This is the IC engine, this is a gas turbine combustor, this is a nuclear reactor, there's a chemical reactor. Heat transfer type, boiler, solid fuel nuclear reactor, heat exchanger. This is the boiler, the solid fuel nuclear reactor, this is the heat exchanger. And the type of the energy conversion device, energy change within the working fluid, nozzle, diffuser, chimney. Yeah, energy change working with this is a nozzle, this is a chimney. Energy conversion to the mechanical energy, piston, turbine, rocket. This is piston, turbine. This is a pump, gear, rotary piston. And mechanical energy conversion to other fluid. Ejector, pneumatic conveying. This is an ejector, this is a pneumatic conveying. Direct generation, MHD, EHD. This is MHD, the EHD. So that so to do the analysis of energy system, the parameter that determine the quality. Usually quality means efficiency of the mechanical to energy to mechanical heat energy to mechanical energy conversion. Quality is you usually saying efficiency. To determine this parameter is a type of cycle. What kind of cycle? Rankine cycle. Rankine cycle, diesel cycle. What kind of cycle you have? Within the Rankine cycle, a simple Rankine and superheat cycle and the reheat cycle, supercritical cycle, ultra supercritical cycle. Within the ultra supercritical cycle, efficiency can go up to almost 40%. Just a simple Rankine cycle efficiency only 35%. So with this ultra high, ultra supercritical, the pressure and temperature of the steam is increasing. Other parameter is the temperature difference of the high temperature to low temperature reservoir. And type of energy heat source, yeah, that's from the nuclear, and that's from the coal, at a different energy source that determine the energy conversion efficiency. The optimization of the component element and entire system and system, there the optimization require mathematical model and optimization ideas. Okay, when you make a model of the energy system, I already said the model energy system is composed of the several different components. Like a previous example, the steam turbine cycle, as a pump and the boiler and the steam turbine and condenser. So if you want to make this component model first, then put together those component system, component model to make a total energy system model. So to make a model of the system component, and widely used model method is the control volume method. So control volume method means this is the volume. Yeah, this is the volume you are looking at it. Yeah, and we usually treat this one as a black box. Black box, once you put in here, and all the inside this all the volume, everything is same. Temperature and all the thing is same. However, more sophisticated volume like a dynamic volume, there's a change. Temperature change within this volume, and that will be you need to consider element of this volume and with the elevation and whatever involved, and the change of the between x direction, y direction, g direction, and you input those things, and you can make a dynamic model. However, we only in here, so thermodynamics, black box model is okay. So we assume that is a control volume model is widely used in thermodynamics because it's all the same, inside is all the same. And system component open system. So the input output same. This energy conservation. What's energy conservation? U equal delta U equal Q minus W, right? So that is a delta Q, that's a heat, that's a work, and there's your input, there's your U value, U1 value, and this is your U2, not, I rather say this is your internal energy, no. That says energy 1, E1, E2. So there's something that in this energy system, let's say it's some, let's say steam is coming in. For example, high temperature, high pressure steam is coming in. There's a potential energy. Steam, here is a high temperature, high pressure steam. Here outside is low temperature, low pressure steam plus water, right? I already said that if we assume this is a steam turbine, then because state 1 has a high temperature, high pressure steam, it has a potential energy, right? That depends on the height. And also the kinetic energy depends on the velocity. Internal energy depends on the temperature. Flow energy depends on the, because steam turbine coming in, there's a pressure volume is changed. So that's four different energy involved in the of the working fluid flowing in, and working fluid flowing out also has the same potential energy, kinetic energy, internal energy, and flow energy. I assume this is steam turbine. I think steam turbine, there's not much potential energy difference. So PE1, P2, PE2 should be same. Kinetic energy may be almost similar. So the same. And something is changed, and only the much difference remaining when you make a model of this individual component. So model of the open system, we assume energy conservation within control volume. Mass said he can move in and out control volume through boundary. That's open system. You know, there is a three different system you can think of: the thermodynamic system, energy system, open, okay, and closed, and isolate. Open system, yeah, energy can be coming out, coming in, and mass also, flow is coming in, coming out. That's open. Closed, energy, only energy can be crossed across the boundary. Mass cannot cross the boundary. Isolated, both cannot cross the boundary. So we assume steady state. Steady state means even the mass coming in. However, mass is always constant. Coming in mass equal to coming out mass. Energy conservation, coming in energy should be coming out energy. So input energy equal to output energy. So that P here, what's the input energy? This one plus all of this. Change the color. Okay. This one, this is coming in, right? This is coming in energy. Coming out energy, if I change the color, this one plus this. So you can write down this equation: P1, K1, I1, Fe1, delta Q equal to this. Then you have this relationship because U plus PV, I equal to, I change the color too. What's I? I is the internal energy, that's U. Flow energy, I say that's a PV, pressure volume of U plus PV, that's H. I assume you guys graduate high school, right? You guys graduate, we are in the graduate school of the Aichi University. You guys graduate, college, 4 years, university within the this science area, science engineering area. You need to know this thing, enthalpy. Even the high school chemistry, high school physics teach it was the enthalpy. So enthalpy U plus PV instead of this one, you put here. So you have this relationship, mg, the potential energy equal to mg, and height, g1 equal height, and the kinetic energy equal to m2 v square, velocity, and h equal to enthalpy of the state 1, and this is the state 2. That's energy conservation equation. So for the boiler kinetic energy, okay, well, what's the boiler means water coming in and steam coming out. Water coming in through the pipe, inside the pipe, steam coming out inside the pipe. So there's not much potential. Maybe energy maybe change, maybe several meters. Yeah, here is the, if it's 0 meter, that's maybe 3 meter. However, that is minimal, so potential energy change is same. Kinetic energy, maybe velocity change a little bit because water became steam. And however, it's within the pipe, there's not much change. So kinetic energy equals same. Boiler is not the boiler is not working. There is no work involved in here. So delta Q, you can calculate mH2 minus H1. That's the one we need when you calculate the steam turbine cycle, Q1 divided by W. So Q1 can be calculated by this equation. Gas turbine or steam turbine, yeah, P2 equal to higher than P1. Steam turbine, I said, pressure can be from 1 atmosphere to 200, 150 atmosphere. So compared to this one is minimal. So temperature is, yeah, gas turbine steam temperature is 650 for the steam temperature at 30. That's centigrade. If you express as Kelvin scale, 300 change to 1000. Gas turbine, the temperature is even higher. So because P1, P2, this condition, so this kinetic energy also potential energy almost same. And Q equals 0 because this is not the heat transfer device. This is the work producing device. So that you can calculate the W equal to this thing, this equation. So this one goes here, this one goes here. You can calculate efficiency. So what's the H1, H2 is it depends on? That depends on the temperature and pressure of the each state. That's the reason why the higher temperature, higher pressure, the efficiency, higher temperature, higher pressure of the steam state, the efficiency will increase. Other model, pump. Pump is incompressible fluid, the volume constant. So also the kinetic energy equals 0, potential energy equals 0. I said H equal to U plus PV. However, volume constant is equal 0. So instead of H, you produce U. U2 equal to U1. So that in this case, the work required from the pump calculate like this. Valve is kinetic energy potential is 0. And once you pass the valve, high pressure fluid became low pressure fluid. So the enthalpy is the same, however, the pressure dropped. Okay, that's we call that. I only show you 4 different components used in the steam turbine cycle: boiler, steam turbine, and pump and valve. However, if you have many different ways, you can different components can be described by this energy conservation model. Previous example is the model of the open system. Model of the closed system, we usually, the example is a piston moving in the gasoline engine and diesel engine. So also within the control volume, only energy can be transferred through boundary, like a piston cylinder assembly or rigid tank. Tank is not moving. Outside wall is not moving. At that case, you use this kind of the energy conservation equation, and for that case, the non-flow work can be expressed like this. And for the piston, you have a piston expansion case, work can be expressed like a U1 minus U2. So, okay, so you need to know what's the U1, what's the U2 in this case, what's the, what's the H1, H2, and what's the H1, H2, H1, H2, all of this. And if so that there is a relationship between the pressure, volume, temperature, enthalpy, entropy change can be determined with the different process and ideal gas law or steam table. For the water, we use a steam table, and gas for the gas using ideal gas law, and process as a isobaric. With a different process, there is a relationship between pressure, volume, the relationship between these things, pressure, volume, temperature, is different with a different process. What that means, if the process goes on the isobaric, the PV, let's say isomer PV relationship. Okay, it's a pressure, volume. Isobaric means, yeah, pressure is the same. So if you change from one, here's a volume 1, this is volume 2. If you change from volume 1 to volume 2, you can go like this. This is same pressure. That's isobaric. Isobar. Okay. Other example, isometric means volume constant. That's if you go down like this. That's isometric. And I think this is isosomer. This is isosomer. And I think this is isentropy. Entropy same. So pressure volume relationship is different. What kind of the process you're taking. So if you know what kind of process you're taking and the relationship between the gas property, like ideal gas law, PV equal NRT, then if you know the pressure, then you can calculate other thing, temperature. So you can get those pressure, if you know the pressure, temperature, and you calculate the enthalpy. Isentropy relationship, you have this relationship. And for the steam, you're using steam tables, saturated steam table, superheated steam table, compressed state, and you need the quality. Quality means the mass of the total mixture, percent of the mass of the vapor. So if you want to calculate the enthalpy, you calculate this. This is water. If the x equal to percent of the vapor, so x equal to percent of the mole fraction of the vapor, 1 minus x equal to mole fraction of the water. So 1 minus x multiplied by enthalpy of the water plus x multiplied by enthalpy of the steam. So you can calculate like this. Irreversibility energy loss. Reversible process means thermodynamic reversible process means completed reverse every change of the press by addition, subtraction of the heat or work without external energy source. Okay, reversible physically, physically piston is moving like that. Piston, here's a piston. If you put the stones, very small stone, gravels like that, and piston is moving, adding continuously, the stone is moving down like that. If you take out these stones and it going back to original state, that's reversible. It never reaches in real situation because there is always friction. The real process is the irreversible process because of friction, heat transfer, and mixing, and the throttling. So how much different from the real process is, how much deviation from the ideal process, you can calculate those deviation amount is through the entropy calculation. So the entropy delta S expressed like this. So increase of the irreversibility caused by entropy increase and decrease efficiency. So the optimization of the energy system means minimize entropy change or minimize irreversibility. Okay, I mean the energy system, if you want to analyze, or especially in the design of the energy system, you need the engineering. Engineering is the, I say, for example, I already explained to you, the engineering is the manipulation of the nature to create system for benefit of at least some segment of the human. Okay, uh, if you wanna build a hydropower power plant, and you know the water flowing from the higher state low place through the river, that's nature. Okay, nature. Then you make a dam. You make a dam here topside and uh, make put the turbine and produce electricity, produce hydroelectricity. And to do that, you need to decide how is the height of this dam through the bottom position, and how much this dam uh, how much of the dam reservoir space, and where is the rotor, how much uh, rotor produce electricity, where is the rotor is located. This is your engineering. So you can express it. So another saying, engineering is the redistribution of the energy resource for something valuable. So when you redistribute it of the resource involved decision making. So we can decide by this is 10 meter or 8 meter. If you want to make this one 10 meter, and the cost maybe 100. If you make this one 8 meter, cost maybe 50. Okay, then 10 meter, 8 meter, 10 meter produce more energy, 8 meter produce less energy. Yeah, that's all. That's all engineering. Yeah, calculating the benefits. So decision-making process we call that design. Design is irrecoverable allocation of resource. So when you make a design, it's very important. Once you done on the nature, you cannot recover. So this is the decision-making process of a new idea to the final stage. If you have a new idea, and once you then new idea, and you define the define the I mean opportunity. Define need. This is a need or opportunity. Okay, if you know, yeah, you have a small town, and you have a small town, and you don't have electricity. Then you wanna build a small unit, small gas fire. Yeah, I mean, yeah, let's say biomass gas fire, gas gas fire, biomass gas fire gas engine system. I said that's a need, opportunity. Okay, opportunity means you have enough capital cost, you have enough money, you have enough uh, technical, uh, technically you have enough ability. That's opportunity. Then you determine the specify the criteria of success. Criteria of success. If you this is the private project private business, yeah, then maybe you can calculate how much of the return, how much of the investment capital cost, how the ROI, return of investment, how much it take, how long it takes to get all the capital cost. That's if it is a private project. However, if it is a public project, public choice is more important. Yeah, public choice you must satisfy all the people living there, right? So even if it require more cost to sustainable goes to the sustainable way, put the more control equipment, pollution control equipment, and if even that cost more, then it depends on the criteria success is different. Then determine the probability of success. Yeah, if there is a very low success, define the needs of the easy. Something complicated. I said criteria success for the in I mean private project is money profit, public project public satisfaction, and probably the success at the after preliminary design is a very low success. Okay, then product design after complete design is much success, and after construction like this, after 1 year, after 5 years, it's a success. Return of investment about this much every year. So through the engineering, how you go this one from this very broad graph to the very narrow graph, that's as engineering can be should be do. Then you do the market analysis. Yeah, if the low probability is a drop, then high probability go to market analysis and design, and then you go to the design and cost estimate and feasibility and availability, capital investment, land, labor, zoning, regulation, and safety code is extra, all of those things, and research and development also. Then research and development and feasibility study takes, if it's feasible, and goes through research and development and go back routine several times, and not feasible drop. That's the engineering way, engineering method from the new idea to the finalize. Okay, so design and research and development, demonstration and iteration, decide go, no go, and finalize the construction, and optimize the operation. So within this optimized operation, should optimize the operation to reduce the cost. Okay, I say at the first time, I most of the what I'm saying this lecture is analysis of the energy system. Okay, well, how you do this? You make a model first. Model, individual component model first, and put it together for the total energy system. An individual model usually based on the energy conservation. Yeah, first law. Okay, first law. So you can make some kind of equation of the individual model, then they put together of the individual component model. You can make a energy system model. Once you make this model, and you can refine this one into the research and development. Maybe this component, maybe you can change into the more efficient one. You can change this component more efficient one throughout the research and development. You finalize through the engineering sequence. Okay, this is the end of this lecture. I think I put some homework. I mean, okay, this is the whatever. I think the homework may be, yeah, whatever you just define by yourself. Define energy system. Define energy system. Whatever your own energy system, and define the energy system and description of the describe the energy system, and second one is how you analyze the energy system. That's homework for this first day. Thank you.